Hi everyone, what's up? Today I want to go over the Fundamental Theorem of Calculus. So usually we abbreviate this theorem by writing FTC, okay? That is the first thing you need to know because it's kind of annoying to always say the Fundamental Theorem of Calculus. It's better to just say, FTC, okay? Now we also write D1 because there are two fundamental theorems of calculus and we're going to go over the first one today. So yeah, let's begin. So the FTC basically says that if you have another type of integral, I'm assuming that if you're learning about the FTC, you probably already know about indefinite integrals. And now I want to introduce a new type of integral that is called a definite integral, okay? So now this theorem, the FTC, allows us to compute the value of definite integrals, okay? So let me show you what a definite integral is. So we can write the integral sign just as you normally would. Now we're going to have our integrand, which is going to be f of x. We're going to integrate with respect to one variable, which in this case is going to be x. And now we can use an integral not only to find the antiderivative of f, but also to find the area under the curve of f, okay? So let's just say we have this plane, and let's say, well, we have some curve like this. Now let's say, of course, this is going to be f of x. Now, what if I asked you, let's say this is A, and before I ask you something, let's say this is A and let's say this is B. Now, what if I asked you, what is the area under the curve of f of x from A to B, okay? That is a question that I could ask. And now you can see that this area, it might be kind of hard to compute because, well, the top of this kind of rectangle is curvy, okay? So, well, you cannot really use any formula that you already know to find the area, or to find this area, okay? To find the area under the curve of small f. So what can we do? Well, we can use an integral to find this area. Now, what's the notation for that? Well, we're going to use an indefinite integral, but we're going to add bounds, okay? Or integration bounds. So a bound is going to be a number that you write here in the bottom. So this is going to be x equals a. So this integral, this antiderivative, is going to be evaluated starting from x equals a all the way up to x equals b, okay? So basically the way we represent bounds, or the interval over which you want to find the area, okay? So the way you represent that is by writing in the bottom of the integral sign the lower bound, which is going to be a in this case, and in the top you write b, okay? This is the notation. And now how can we compute this? Well, the FTC tells us that we can compute this by finding the antiderivative of f, a small f, okay, which is going to be big F, and we can evaluate big F at b, and then whatever this is, we can subtract from that the antiderivative of f evaluated at a, okay? So this is the fundamental theorem of calculus, this equation, and it basically allows you to find one thing that allows you to find, I should say, that you can compute more than just areas using the FTC, but one thing that allows you to find is the area under a curve, okay? So if you want to find this region, this area, well, how can we do that? Well, we can use the fundamental theorem of calculus, just set up our integral, and then just, find the antiderivative of f, which I should highlight that here. If we have f prime, big F prime of x, well, we know this is going to be equal to f of x, okay? Small f of x, okay? So this is the relationship between big F and small f. So this is basically the FTC. I'm pretty sure you've seen this integral notation before. It's pretty common, So yeah, I hope this has been, easy to grasp. Now I want to go over some quick properties of definite integrals, okay? So let's do that. One of the most important properties of definite integrals that you need to keep in mind is going to be this one. So if you have the integral from a to b, in the previous example, I wrote x equals a and x equals b. You don't have to do that, I just wanted to emphasize that the inputs for our integral are going to be x equals a and x equals b, okay? But you don't have to do that, so you can just write a and b, okay? So if you have the definite integral of a polynomial or a binomial or anything that has more than one term, so say you have f of x plus g of x, if you have this integral, well, this is going to be the same as the definite integral from a to b of f of x dx plus the definite integral from a to b of g of x dx, okay? So this is going to be the first property, and this property is really useful because a lot of functions that you'll encounter in calculus are going to be polynomials, okay? So if you have the definite integral of a polynomial, just take the integral of each term and that's it, okay? So now another really good property is that if you have the definite integral from a to b, this sign looks kind of bad. Let me try to fix it. Yeah, that's better. So if you have the definite integral from a to b of c is going to be a constant, you know, any coefficient, times any function f of x, well, you can compute this integral. And of course, I should have mentioned up here that, you know, the way in which you compute these two definite integrals is by using the fundamental theorem of calculus, okay? So I didn't write that here, but I think that's pretty obvious, okay? So I didn't mention it, but yeah, keep that in mind. So how can we compute an integral of this form? Well, once again, we're going to use the FTC, but something that you need to keep in mind about c is that c is a constant, so it will not affect the integration. Remember, I'm assuming you already know anti-differentiation. So when you have a constant, this constant will not affect, I mean, it's not that it won't affect, but you can take it outside the integral such that you can such that your integrand looks simpler, okay? That's my point. So this definite integral, you can compute it by taking c outside the integral sign and writing c times the definite integral from a to b of f of x dx, okay? So this is another property. Once again, you can just simply take out c, okay? And that is going to be the result that you're looking for. So now another property which is really helpful, and it might be kind of obvious once you see it, but if you don't see it, you know, written on a board, you might not be, you know, you might not come up with it, you know, instantaneously. So this property says that if we have the definite integral from a to a, well, what do you think this is going to be? We have the function f of x dx. This is going to be equal to 0, okay? Because this is going to be the antiderivative of a small f evaluated at a minus the antiderivative of a small f evaluated at a, okay? So this is just going to give you 0 at the end of the day, okay? Let me fix that, yeah. So this is just going to be 0. This is, you know, pretty obvious once you see it written, but it's, you know, it's worth mentioning. And also, you know, if you want to see it from a graphical perspective, this antiderivative is, well, is the way in which you would compute the area between a and a. So basically the area of a straight line and, well, a vertical line. And that makes no sense, you know, this is, if you have a line that's one dimension and you need two dimensions to have an area. So that is why this area is going to be 0, okay? So you can, you know, you can imagine the geometric picture of this definite integral, okay? So let me erase this property on top and let me show you another really cool property which is going to be really useful and you're going to use it a lot. So if you have, let me just write for a is less than b and b is less than c, if you want to find the definite integral from a to c, once again of our function f of x dx, well, one way in which you can do that is by, and I'm going to show you a picture of this in a moment, but let me just give you the formula, you know, let me just show you the algebra. So this is going to be the same as if you had the integral from a to b of the function f of x dx plus the definite integral from b to c of the function f of x dx, okay? So now I hope that just, you know, just by seeing the equation, you can geometrically imagine what is going on. Pretty much, you know, we just have some graph, which I'm just going to say it's something like this. We can say this is A, let's say this is B, let's say this is C. You can, if you want to find the area from A to C, well, you're going to have A1, which is going to be the area from A to B, and then you're going to have A2, which is going to be the area from B to C, okay? This integral is A1, and this second integral is going to be A2. Now, if you add A1 and A2, well, of course, you're going to get the total area, and that is going to be the area from A to C, okay? So that is, you know, that is the geometric picture that this equation conveys, okay? So that is another property, and I said that you're going to use this property a lot because when you use substitution to compute definite integrals, there is a rule that is actually not well known by most people, and it is very important. If you use substitution and you use u substitution, let's say u is going to be the variable that we use, and u prime is a derivative that changes sign over the interval from a to c, well, you're going to have to compute two definite integrals because u prime changes sign, okay? That is, a condition of change of variables, and that is something very important, and the only way you can, get past that problem is by using, by splitting one integral into two integrals, okay? So this property is very important, and it's also, I think, very intuitive, why am I erasing it? Well, yeah, anyways. I'm erasing it, I should have not done that, but yeah, the property, you can, go back and see that. So I'm gonna erase this, and let me show you another property. So the last property that we have many other properties, but the last one that I want to show you today is that you can have, let's say, once again, we have the definite integral from a to b of the function f of x dx. Now, there is something really nice about this, and how should I write it? Yeah, I'm going to write it like this. This definite integral is going to be minus the definite integral from b to a of the function f of x dx, okay? Now, this may not seem intuitive graphically because we're saying that, when we write this integral, we're assuming that b is greater than a, and it is very counterintuitive to find the area from b to a when b is greater than a, okay? Now, that doesn't really have any geometric interpretation. However, computationally, this makes sense, and I'm going to show you why. So we know I'm going to write it like this. So we know the left-hand side of this equation is going to be the antiderivative of small f, which is going to be big F, minus big F evaluated at b minus f of a. And now, what is going to be this, the value of this integral? Well, we know that it's going to be, I'm going to leave some space, so we know that it's going to be the antiderivative of small f evaluated at a minus the antiderivative of small a evaluated at b, okay? Now, you can see that if you multiply by minus, I'm going to write that in red, if you multiply by minus 1, this subtraction, well, you're going to get back to this subtraction right here, okay? When you distribute this negative 1 into these two, well, you're going to get, once again, big F evaluated at b minus f of a, okay? Which is exactly what we have on the left-hand side, okay? So, computationally, this is a property of definite integrals. Now, geometrically, I know in some more advanced math, there might be a way to describe this. However, I am personally not familiar with that math content just yet, so I'm not going to say anything. But I can tell you 100% confident that this property is true, okay? Computationally, you can see that it works out. So, this is a property that you can learn and you can use, okay? So yeah, I would say that's been the entire video. I hope that you enjoyed it, and see you in the following one. Bye.